Unit 3, lecture number 3. So here we will discuss about intermediate code generation. So the intermediate code generation can be understood using this diagram. So this is the logical structure of compiler front end, and the back end is associated. So intermediate code is the last part of the front end. So what happens here? So you can see in the diagram, in the front end we have a parser, and the output of parser is connected with the static checker, and that output of the static checker is connected with intermediate code generator, and this intermediate code generator will produce the intermediate code, and finally it is provided to the code generator, which is the part of the back end. So the static checking includes type checking, which ensures that the operators are applied to the compatible operands. Static checking also includes any syntactic checks that remain after parsing. For an example, static check ensures the break statement in C is enclosed within the while for switch statement. An error is reported if such an enclosing statement does not exist, etc. So, in the process of translating a program in given source language into code for a given target machine, a compiler may construct a sequence of intermediate representation as in the following figure. So, this figure you can see that here we have a source program. That says program is provided as an input of the high level intermediate representation, and it may move through different number of levels, and finally low level intermediate representation can be there, and finally there will be the target code. So a compiler must use the sequence of intermediate code representation. So high level representation are close to the source language, and low level representation are close to the source language, and the low level representation are close to the target machine. So variants of syntax tree. So we need to understand about syntax tree, because for writing the intermediate code we will use the syntax tree. The node in syntax tree represents the constructs in the source program. The children of the node represent the meaningful component to construct. A directed acyclic graph for expression identifies the common sub-expression of the expression. So directed acyclic graph for an expression. Let us take understand these things that and the directed acyclic graph has leaves corresponding to atomic operands. This is the minimum operand. That suppose you write 4 plus 6, so 4 will be at the leaf, 6 will be at the leaf, and plus will at the plus with the parent of the 4 and 6. So difference is that the node n in a DAG has more than one parent if n represents a common sub-expression. In a syntax tree, the tree for the common sub-expression would be replicated as many times as the sub-expression appears in the original expression. For an example, let us consider this expression a plus a multiplied by b minus c plus b minus c multiplied by d. Here we can see that b minus c is repeated two times. So this diagram you can see here, this is the directed acyclic graph here. So a minus b is here, and this a minus b value is used for the d, as well as this is also used for the a. So for we are multiplying this a with b minus c, and we are using b minus c multiplied by d by using the only one b minus c operation. This a is also used here, so a is repeated here. So a plus this value will be here, and a plus final value is here. So this is the DAG representation of this one. Let us consider about the semantic rules. What are the semantic rules? So e arrow e plus t e node. So you can see a new node plus operation is to be done, e1 dot node and t dot node. These two values should be applied for the plus and then for the minus. So these are the things here. The parenthesis, we need to parenthesize here. T arrow id must be here. So all these production semantic rules will be associated with it. So let us try to write all these things. P1. So what is P1? P1 is the leaf of id in tree A, because we are giving here as a leaf part. Similarly for P2. P2 you can see here. Here we have entry A for the B part. Similarly for the P3 we entry B we are taking C. Since A was used at two times, so we have taken two times here. Okay, now what we are doing, p5 equal to node minus p3 minus p4. So what is p3? P3 you can see p3 minus p4. P3 is here b, that is b minus c. The value of p minus b minus c is here in p5. Similarly for multiplication, p1 multiplied by 5. So this part is multiplied by P1 into P5. Similarly, for addition operation is done. So it is according to this diagram. And finally P9 we have the entry. So P3 and P4 we are just repeating here. And again we need to subtract here for the B minus C. And finally we get the result in P13. So this is the steps for constructing the directed acyclic graph as it is in figure 6.3. So the sequence steps of shown in figure 6.5 here. So this is the 6.5 diagram. So we construct here. So this is the description here. When we call leave id entry comma a, so it is repeated at step 2. The node is created to the previous call is returned. So p2 is equal to p1 here. So here you can see in the second part p2 equal to p1 here. Similarly node returns at step 8, say 8 and 9, so are the same thing, that is in 3 and 4. So P8 and P3 both are same, P9 and P4 both are same. Hence the node return at step 10. So in step 10 P10 and P5 both are the same. So these things are repeated here. Now value number method for constructing directed acyclic graph. Let us consider one example. That example is that I equal to I plus 10. So we are so I equal to I plus 10. So what we will do, the node of the syntax tree of the directed acyclic stored in the array as the records of the suggested here in figure 6.6 here. So each row of the array represents one record, and therefore one node in each record. The first field is the operation field. So this is the operation field you can see here. uh, in each record this is the operation field indicating the level of the node. Figure 6.6b. So this part we are talking about, this part, the leaves have one additional field which holds the lexical value, that is symbol table pointer or constant, and the interior node have two additional field. So two additional indicating the left and right part. So this is the id. Here we have entry for I for num equal to 10. So 1 plus 2, 1 plus 2, 1 is id, and 2 you can see this is the num, so id plus num. So this is 1 id plus 10 we have here. Id can be I here, and this is assigned here 1 equal to 3. 1 assignment operator here. So 1 is I, that is the id equal to 3. This is 3 equal, see, this is the addition 1 plus 2 part. So this way this part is shown here. So it's very simple to understand. So we will take one construct DAG for this expression. So all we have two examples. These two examples you can take for yourself, that is a homework, and you need to complete that part. So now three address code. The three address code is there is at most one operator at the right hand side of the instruction. There is no built up of arithmetic operation permitted here, and the source language like x plus y multiplied by z might be constructed into the sequence of three address instructions. So how we can write? We can just write like this: t1 equal to y multiplied by z and t2 equal to x plus t1, where T1 and T2 are compiler generated temporary names. So compiler can generate the temporary name T1 and T2 here. So in this way it can be done. So in three address code we have only one operator. So you always remember that we have only one operator at the right hand side. Three address code is a linearized representation of the syntax tree of the DAG. So here we have DAG, and here we have this equivalent DAG here. So this is the three address code here. So b minus c we can write as a t1, then a multiplied by t by t1 we can write here, and this t2 can be added to the a and can be stored in the t3, t1 multiplied by d. So finally we have here t4, and t3 plus t4 result is in t5. So finally the final result is in t5 here. So this is the DAG for expression, this part a plus a multiplied by b minus c plus b minus c multiplied by d, and its corresponding three address code here you can see. So it's very simple to write the three address code. Next we will discuss in the next class.